maybe that's a clue, because 5 is a lot less than infinity. If we turn it into a literal spherical cow, it has a ratio dimensions that comes out to be the magnitude of the cosmological constant, meters squared. I need your help. What's going on here?
You finally flipped.
So, welcome everybody. All right, so today we're going to be talking about this fun little quote here. It's called the Spherical God Cow, whatever that means. So we're going to go into that, and we have our terribly drawn little friend here that's not quite spherical, but this is a bit of a pun on the whole concept of the spherical cow within physics, because physicists very often, well, we treat it as an idealized condition, even though things are usually never actually idealized.
This is from an old joke that physicists tell each other. A farmer asks for advice from a physicist about how to maximize the milk output of his herd of cows. Physicist goes off and thinks about it, and then comes back a few days later and says, okay, I've got it all figured out. First, assume a spherical cow. Now, to a farmer, that does not sound like a very good idea, a spherical cow, right? Like, cows are not anywhere near spherical. That is a bad approximation. But to a physicist, it makes perfect sense, because that's how physics works, by stripping away all the complications.
Okay, and then I called it the God Cow, of the play on the God particle, because it's something that happens to annoy a number of physicists, even though it was written by a Nobel Prize winning physicist who most likely probably did it to sell more books. So that's where the term comes from, and it's a crazy title, but we're going to kind of go into precisely why I named it this. And also we do have a new shirt for those of us in attendance. Hopefully I did have enough sizes. Mike, I'm sorry, I can order you a couple of more. But basically this just has the equation that I presented over in Portugal on an episode of Paradigm Drift. Again, this is a claim that the elementary unit of action divided by the reference action, you take the square root of that, multiply it by a Planck mass, and coincidentally you get really good agreement within about 4 mega electron volts of the most recent measurement coming out of the CMS detector. For what we're going to be talking about here, don't need that at all. You can literally just go on Wolfram Alpha, do some calculations, and see what we're talking about. Okay. So the whole claim is, what the heck is going on? Now, part of this is, and I kind of wanted Dan and Jim to be here because I know you guys are really both into cosmology and everything, because I play around, I go down so many different Wolfram holes, so to speak, that a lot of them are just dead ends, don't really go anywhere. I feel like I'm just a crazy person. I mean, that's true, but at the same time, every once in a while, maybe you find something that's a gem. Maybe it's just fool's gold. I'm totally willing to accept that to be the case, but I'm going to need everyone here's help once we go through this to try to kind of brainstorm what the heck's going on. So let's get into it. So basically all I did was I took the mass of the Higgs, so just lowercase m, subscript h with 0 because it's spin 0 particle. So now we have a mass. Now it's very often measured in mass energy, so we'll just, for accounting, c squared. So we're taking the mass energy equivalent of the Higgs boson. Okay. Now we're literally going to turn it into a spherical cow. We're going to do 4/3 pi r cubed, and then we're going to do, for our r, we're going to do the I think this is the symbol for the Compton wavelength of the Higgs. That's cubed. So literally we've taken mass energy of the Higgs boson and we are turning it into a spherical cow. 4/3 pi r cubed. Okay. This equals very big number. Big number. In the video, I'll probably just overlay the exact calculations, but just for sakes, it gives you a really big number. Now, this number is in its energy density. So we have energy density. So basically, it's an energy divided by a volume. And we are assuming it is a spherical cow. So I'm like, okay, what do we do with this? Is there anything else within our realm, so to speak, that's important, that has energy density? Well, we happen to have the universe's energy density as measured by Planck and everything. And again, I'm assuming that they measured something, their detectors went click, things seem to work. Okay, I'm assuming that most of physics generally works, and again, there's probably going to be some tweaks there. We know that it's not the final answer, but if we have the density, so we'd have rho vac, and if we take this number, and then we divide it by our little cow here. So if we take the vacuum energy density, we divide it by this spherical God cow, we get approximately 1.1 times 10 to the minus 52. Okay. I look at this and I'm like, wait a second. Why does this number look so familiar? Coincidentally, the cosmological constant, just to spell it right, Cosmo. If you divide this, oh, excuse me, we need to do this the other way. Inversing matters. So, no, actually, this was the right way. So, basically, we get this number. This is a dimensionless number. I was doing it right the first time. Cosmo is approximately 1.1 times 10 to the minus 52 reciprocal meters, so inverse meters. So square meters with a 1 over it. Okay. What the heck is going on? This is why I kind of wanted to present this, because it's like, okay, at one point, little background of the story, one point, probably, I don't know, maybe about a month ago, Professor Sean Carroll put up one of his solo Mindscape podcasts, and in a row he was talking about the problems within physics. He's like, well, you have the hierarchy problem of the Higgs boson. Why is it so much smaller than the Planck mass?
The cosmological constant is, or apparently looks like, 10 to the minus 120, its natural value. So maybe it's not the cosmological constant that we're observing. Maybe the cosmological constant really is zero. Maybe we were right in some weird way, that there is some mechanism that we haven't yet invented that sets the vacuum energy equal to zero. And what we're seeing in the acceleration of the universe is some field that has an almost constant energy, but not quite. Okay? Here's the problem with that idea. We would call this dynamical dark energy, or quintessence, sometimes it's called. The problem is the same as the problem with the hierarchy problem in the weak interactions. The Higgs boson field is a field that pervades all of space, and its mass is small compared to the Planck mass, right? Its mass is 10 to the minus 16, something like that, the Planck mass. And we say that's a small number. Masses in particle physics, under the rules of effective quantum field theory, tend to be big, tend to be driven up to very large numbers, okay? And so the hierarchy problem is just that there's a factor of 10 to the minus 16 between the Higgs mass and the Planck mass. If you have a dark energy field that is making the universe accelerate, it needs to be changing very slowly. Otherwise, we would have noticed a long time ago. If it were changing rapidly on cosmological scales, that would have been easy to detect. It wouldn't even have acted like dark energy. The whole thing that dark energy needs to do is to change slowly so that its energy density is approximately constant and it can make the universe accelerate. So if it's an ordinary, not weirdly atypical field filling all of space, that has some kind of mass. We talk about the mass of a field. What we really mean when we say that is the mass of the particle you would make by jiggling that field. That's what we mean when we talk about the mass of the Higgs field or something like that. It's the mass of the particle you would make.
Again, I would claim that maybe there's a reason for that. That aside, just literally just putting in the words on Wolfram Alpha, and again, it doesn't have the most up-to-date measurements, but to a first-level rough approximation, why the heck should the one, to our knowledge, something that we believe to be the Higgs and have Higgs-like properties, and that's an elementary scalar boson that we believe, according to the standard model, that suffuses all of our realm. It just seems to be everywhere. It seems to help give mass to other particles. That is what we believe it does, and we believe it's everywhere. If we turn it into a literal spherical cow, it has a ratio dimensions that comes out to be the magnitude of the cosmological constant. If you divided these into each other, you would basically get a difference of, depending on which one you divide it into, meters squared. Which is an interesting thing because as we played around with some toy models, that seems to be the difference between different ratios. It's just meters squared. Guys, I need your help. What's going on here? Thoughts, comments?
Question.
Yes.
How many more digits is this true for?
This is, okay, full disclosure, I'm writing it about, it has the correct magnitude. The cosmological constant depends on the data set you adhere to. So it appears that if you would include supernova data from farther and farther away, that number, that 1.1 can go up to, I think I calculated about 1.4 or so. So that's part of the crisis in cosmology.
So we don't even exactly have a nil down constant for it. So if you, as well
Yeah.
as you can tell with the data right now.
Yeah, so generally this number has pretty good agreement with like the Planck survey and things that are closer to us. So unless maybe universe is rotating, which I'm a little bit partial to, but I don't know that's the case, or unless there's a very good estimate or explanation for why our data starts to deviate at greater and greater distances. I just thought it was very interesting that it seems to, like, basically this is kind of the lower end there. This actually comes out to be, I think about 1.083-ish, something there. So it seems to have pretty good agreement with what we believe to be the cosmic microwave background. I mean, I just saw this. I did a calculation. I'm like, wait a second. That's not basically the magnitude, because Wolfram Alpha rounded in there. So I'm like, it literally gave me 1.1 times 10 to the minus 52. And then you type in cosmological constant. It gave me 1.1 times 10 to the minus 52 reciprocal meters squared. And I'm like, that's weird. So, hello, sir.
Hi.
Did you have questions, comments?
Yeah, I have a comment. I noticed that the spherical God Cow is not just a sphere, it's a ball. It's full, right? It's not just a shell, it's full because you're using R squared. And then as you're doing your math...
R cubed.
R cubed.
Yes.
Sorry. Yes. So when I think of the full ball, I also think of the boundary of the divergence in the ball and the flux through the boundary. And the boundary is going to be a square thing instead of a cubic thing. So you might maybe somehow have seen something going through a boundary of the spherical God Cow. So maybe the spherical God Cow's skin has something to do with this meter squared thing, and the spherical God Cow's body has to do with the Higgs mass. But that's so far removed from reality, I have to call it complete, utter speculation. Utter speculation. So take that for what it's worth. Thanks.
Okay, okay, yeah. All right. No, thank you, sir. Thank you, sir. I mean, hopefully, I am of the opinion that observers like us, human beings, we should be able to figure this out. Maybe not today, maybe not tomorrow. Who knows? Maybe Wednesday or Friday we'll figure it out. I couldn't say. But yeah, I just did this calculation. I'm like, wait a second. And I think, was it Professor Carroll or anything? He said something about it's like, oh, you have these differences. Oh, they get this magnitude or something. I don't think maybe he said they were of a similar magnitude, but it would depend upon your units and everything there. I just generally use the 5 general bases that is laid out: time, space, mass, charge, and temperature for my own parameterization, because I'm like, well, if we can reproduce our observed values using only 5 bases, maybe that's a clue, because 5 is a lot less than infinity. So
This is really cool too, because I mean, we only know it so far to 2 digits and the power. Let's not forget, so that really improves the match. But the statement is really nice and clear. You're just saying the energy density of the vacuum divided by the energy energy density of the Higgs, right, is equal to the cosmological constant times by a meter squared.
Yeah.
That's a pretty clear statement. So that's a nice prediction right there. But it's also awesome because in 2 cases now, you're using the mass relationship with the Higgs on your shirt and there, right, to show a perfect coherent exchange with the bases themselves. I mean, the one on the T-shirt has bases in joules and seconds, right? This one now has meters, right? So
it's
at least that they go together. So
So I'll ask the counterfactual question is, when they built the machine to measure the mass of the Higgs, did they inadvertently look for this mass? One thing physicists have been very good at is finding what they're looking for.
So to my knowledge, yes. Okay, so when I looked into that, initially my knowledge is we saw signs of it at the Tevatron, and I think they said it was between like 110 to 165 giga-electron volts. They saw a bit of a bump in the data, because basically you're looking at the data, it's doing its thing, you have a spike, and we often attribute that to what we tend to use the term particle, whatever that may or may not be. Basically, at the Large Hadron Collider, we turned it on, it blew up, we fixed it, we turned it back on, and then both CMS and the ATLAS experiments, they found it somewhere between, I think, towards the upper end, around 125 to about 126.5 GeV, because before, like, it was a very large range. So they eventually saw bumps there, and then I think like the most recent measurement from like CMS was, and there are some error bars here, but it was 125.38 GeV divided by c squared, so we get our mass out. This is just an easier number for me to remember. And then just for shameless self-promotion, if you plug this in and you do the calculation, so this would be the shirt calculation, gives you 125.376 with an error of 2 in the last number due to the uncertainty of the Planck mass, just according to physics as we know it, GeV divided by c squared. So that's why I looked at that number. I'm like, all right, there's no way. But again, this is based upon the shirt. This, you can basically just plug into Wolfram Alpha. You're getting the magnitude. Again, it's dimensionless. But I'm just thinking, I'm like, wait a second. If we don't know why these things are going on, it's like, if we have at least one, according to the standard model, elementary scalar boson that is everywhere, that has some value, I'm like, somebody had to do this. Like, I mean, like, isn't this like just like physics homework or something like this? Like, do some.
It makes me wonder about applying it to all the rest of them. So put every other mass boundary in that same equation.
Well, that was okay. I actually
and look for any other sort of relationship in physics they might characterize. Because if it's a pattern, then it's much easier to try to make sense of.
Thank you. That reminded me. My first thought is, number one, I did something wrong. Okay, so go through, double check the calculation, it comes out again. Then my next thought is, this has to be a trivial thing. I'm sure, like, if I put in the electron mass and the electron's radius, like, kind of like that little thing where things seem to equate out to h bar, I'm like, all right, this is just going to be one of those things that'll hold, because that mass will get smaller, this will change there. Crazily, it didn't seem to, for at least the things I checked. I haven't checked every particle and stuff yet, but I tried the electron with the classical radius, the Bohr radius. I did the proton was within about 1 or 2 orders of magnitude.
I was expecting those, since it works for the Higgs, the ones that are most likely for it to work for are the W and Z.
Right. I still, to be fair, I actually didn't even do that. I was just partially lazy there. I'm just assuming that
But so far you did check a few and it didn't hold for them, so it's a special case. Well, at least we didn't know what it characterized or didn't find something.
Well, part of the reason why I used the Higgs, and again, that was just further investigation on my part is required, but the Higgs itself is basically of the magnitude of the range of the weak force. The weak force is approximately 10 to the minus 17 meters. When you do the calculations for its wavelength, it's like 9.880 or something like that. So it's literally the range of the weak nuclear force there. So just, I did this and I'm like, well, if this has an energy density, and I just assume idealized conditions, we literally turn it into a spherical cow. I'm like, somebody has to have done this.
Is the Higgs the highest one?
No, top quark. Well, actually, the other interesting thing, which isn't really for the scope of this lecture, but one of the things that we had noticed is the distance from the Higgs boson to the Z boson and the top quark seems to be the same magnitude. So basically, if whatever factor you divide the Higgs by to get down to the Z boson's mass, if you multiply it by that same factor, it looks like it's the same factor. And I think, what was the factor I used? I think it's literally to go from the Higgs, so mass of Higgs to the Z boson. I think it literally is a factor of, I think it's E 1 over pi. Or e raised to 1 over pi. And I forget if I either need to multiply or divide by that, but that coincidentally gets you to the Z boson within 1 standard deviation of error bars, as well as it fits the more recent measurements of the top quark pretty well. And I have no idea if that's a thing. I've seen that before, but I'm like, okay, how can I justify it? Because I'm trying to match the data as well as I can. I had some other factors. The other thing that kind of got me to that is ultimately I actually was using AI and actually like ChatGPT with the Wolfram plugin and stuff because some notation is, I'm not a mathematician, so if it could explain it clearly to me. So basically when you calculate the self-interaction of the Higgs boson, when I did plug in the number from the shirt here, it gave me a Higgs self-interaction, or at least the best fit to the number of decimal places it output. So the H not self, so it's self-interaction. The best fit I found was 3 over e to the pi. So e to the pi coincidentally happens to be the factor for all even unit dimension hyperspheres. And I'm like, let's divide by 3. I'm just like, I'm like, okay, that's an interesting thing. And again, that is assuming there's some there with this calculation, but it matches for I think 5, 6 decimal places, something like that. So because the main thing I'm trying to do is I'm trying to find something we can latch onto with a high confidence that has maximal explanation value, and then because if we can latch onto like some mathematical constant, then we should be able to backtrack and just double check ourselves. And it's multiple layers of being able to check. So it's like when that has a calculation, I'm like, all right, let me see if I can replicate this from another point of view. Kind of like, well, the fine structure constant, you can do elementary charge squared over 4 pi h bar c epsilon naught, all that jazz. I'm like, okay, maybe I can tell a story for that, or I could computationally reduce it to elementary charge over Q sub T, Planck charge. You square the whole thing, and I'm like, this gives you the fine structure constant as we know it. Without squaring it, we get J1, or the amplitude of the fine structure constant. And that's literally, I just took that intuition, and that was all I did for this, because all I literally did was going to Wolfram Alpha. It's like, all right, we got mass of a Higgs, divide by the Planck mass. You get 10 to the minus 17. That's the hierarchy problem. Why is it 17 orders of magnitude? Yes.
Yes. This morning, my YouTube algorithm showed me Lenny Susskind, a little short, and he was defining what the Planck mass was. And he said, the Planck mass is the mass of the smallest black hole. Boom. And that's right. And if the Higgs mass is much less massive than the Planck mass, that means that the Higgs particle is not a black hole. It's simply maybe a little tiny piece of a black hole. Or when I get more into my findings, I have a way to kind of divide up the Planck mass into little tiny pieces. And when I do that, it starts to look like quantum mechanics energy of the photon. So Higgs is just not a black hole.
I agree with that. That seems to be what it is, and I'm of the similar mind. To my understanding, it's the maximum mass and within a minimal volume, as far as we know, you're going to create a black hole, and therefore the Planck mass would be a minimal black hole. So that's my understanding too. So
no, it's not, well,
Yep.
Well,
I know there's a caveat. There's a factor or two in there for some reason, and
it's the minimal persistent black hole.
now do we not assume evaporation there? Because I could go either way on that. I have no idea what happens, but then again, at the same time, I'm like, that always confused me because it's getting antiparticles, but do we know it's getting antiparticles? Yeah.
What if there was a kind of black hole that didn't persist very long?
That's interesting.
Well, the smaller they are,
We'll get to that later.
That's something to chew on. Okay. We don't need to spoil any of your stuff, Rick. So, okay, cool.
What is the symbol there?
Which one?
Cosmological constant on the very.
That's a lambda. It's supposed to be for like a wave. I might be just getting this wrong because this is basically usually something for wavelength.
Yeah. So what are you saying there? That the
They call it lambda. Oh, actually, no. I actually did get that notation wrong.
lambda of the cosmological constant is.
I just use that to represent it because usually they just use. Actually, they usually just use this. So I apologize. I actually used the wrong thing there. That was for wavelength. This is the lambda as far as.
And what is your question? Why do we have this n squared? You don't know what it represents. Is that what you're saying?
Oh, this guy over here. This is meters squared. That's the unit of meters. So sorry, I should write that out because we got small m over here. So from convention, you would think just an inverse mass square. So yes, this is approximately meters inverse meter squared. So I actually would just write this.
What was your question about that? Was there a question about that?
So it was I have a little toy model I've been playing with that I'm like, okay, would there be a way to potentially estimate mass of universe, so to speak? So I remember it was originally, I think, Dr. Salvatore Pius, and I think Rick may have mentioned something like this when he was here, that perhaps we could use the Planck force as a constant of proportionality. Because if we take our generalized measurements of universe as we see it here, I'm using small u because I don't know what might be outside the realm, so to speak, if that was the case. But basically, if you look at it and you take the radius of the observable universe and then you divide that into the mass energy of the observable universe, you're going to get out, I believe, the units of force. And it's really dang close to the Planck force. So I'm like, again, what if I assume that was true? So that has an estimate. I'm like, Well, if I take Thad's madness seriously, again, no offense, but if I take the model seriously, what would be the consequences? Well, the inverse of the Planck length is a really big number. So I just put that number in for the radius, do the calculation, come up with like a 10 to the 61 kilograms, ginormous number, and then I found a way to computationally reduce it, which was, this box over here, that's the wrong marker, but basically all I did was just take literally meters, that was the bad marker, meters over the Planck length squared Planck mass. So I just took I divided the dimensions out, so all I did was take the meter, our defined unit of length, now by the constants of nature, thank you SI, divided by the minimum length to our knowledge. I squared that ratio, you multiply it by the Planck mass, and that ends up being equivalent to assuming that the Planck force is a constant given our size of our realm.
The Planck force?
Yeah.
Planck force shows up in general relativity.
Yep, 8 pi divided by the Planck force is literally Einstein's kappa constant. Oh, thank you, Rick. That reminded me. Let me just do this guy.
He was trying to come up with a model to calculate the mass of the whole universe. So we're trying to get some way to relate the math in the small.
I forgot what was I just talking about. I'm sorry, brain fart.
Planck force?
Oh, yeah. So this whole, yes. All right. So if we take our cow, again, poorly drawn cow, and then we multiply it by that kappa. So this is the Einstein kappa, and this is the C4 convention. So speed of light to the fourth. When you multiply these together, you basically end up getting, it is like 1 over meters squared. Because that's why it seems to be, because, yeah, the Einstein kappa is like 2 times 10 to the minus 42-ish, somewhere in there. And then this number is very close to the inverse of that.
Energy density is the stress energy tensor, T mu nu in general relativity. When you multiply by Einstein's kappa, you get G mu nu, the gravitational tensor, Einstein tensor. So what you're showing me is, oh, that's how much gravity there is.
Cool. I'm still working to try to grok my head around. That's why I kind of want to show this to you all. So I'm like, help, please. What the heck is happening here? Because I can notice a coincidence, but it's like, even if you calculate something, you get the number. Number one, how much of a kludge did you use? How many epicycles did you add in? Because you can automatically get whatever number you want if you add enough. So I'm attempting to, within the spirit of the Wolfram Institute, let's say, I'm attempting to computationally reduce things into a minimum form. And at least if I can simplify it, maybe some noob like me can try to get some insight or go to smarter folks like you all and be like, what's happening? Because I could just say, I'm like, well, if this is the elementary thing and it fills up all that space and everything or whatever that might be, and it seems to be about the magnitude of something that we're not sure about, why might that be the case? And I don't know, as the cosmological constant is it constant? Is it an observational effect? Because when you take the square root of that, coincidentally, you get about the radius of the observable universe. So I don't know, I think a lot of this, and I think Jim was talking about this a little bit earlier, like how many assumptions when we're doing our analysis are we baking in? And are we even conscious that we're making these assumptions and we haven't because our assumptions can be wrong. I mean, we're meat bags, we're perfectly imperfect creatures. So it's like, if we bake in an assumption, that might lead us astray. Sometimes maybe we should take a step back, look at the actual data, because, well, if we have 4 pixels for what we believe to be a supermassive black hole, and all of a sudden we show this high-res image, it's like, is that what we actually saw, or is that what we're assuming is going on? So that's one of the things where sometimes I think, sometimes you take a step back, maybe have a fresh set of eyes, and that's also why you're supposed to have blind studies in science. So people aren't talking back and forth, and we know they're totally not talking back and forth. So
You're going to milk that utter speculation for all it's worth.
yes, yes, I see what you did there. Yeah, this is about, just to finish this guy. This was basically what I did to do the little shirk calculation. I just took that, if you have an elementary unit of charge divided by a Planck thing. So elementary unit divided by a Planck unit squared gives you the electromagnetic coupling constant. I'm like, all right, elementary unit divided by its equivalent Planck unit squared, and it seems to be about the magnitude of h bar. And if you want it to be correct, you would divide it by the reference of action, joule, which is the SI unit of energy, seconds. And this was the hard thing I had to justify for a while, because I'm like, I'm just kind of inserting that, and that just seems crazy. But upon investigating units and now seeing that units themselves are literally, to be fair, they're actually doing something very similar. Like for the meter is literally numerical value of speed of light divided into the speed of light outside the brackets times seconds, because seconds is now defined as basically the frequency of cesium-133, and now everything is at least referenced by constants of nature. Is that the optimum way to do things? I don't know, but at least at this point, now our base units, as well as their derived units, are at least based upon constants of nature themselves that we have measured to whatever precision. Our device went click, and we interpret it as this. So I am assuming that much, if not most all of science actually works. These are the assumptions here. Is this the actual story? Is this the ultimate answer? I can't say, but yeah, that's why I just wanted to share this with you all, just so I'm kind of get leverage additional consciousness to try to parse this. So,
well, I have a question, but it kind of backs up.
no, please.
When I think of the Higgs,
yeah,
it makes sense to me as the field. In fact, it makes sense to me as the substrate for the entire universe, right? If there would be an ether, in my mind, I see it as the Higgs field.
That's what I see.
You see it
a
too?
crystalline ether. The density and the elasticity determines the speed of light. That's why light can change.
It depends on the medium, because we say the speed of light in a vacuum, quote unquote. So yeah, well, that's.
This is the way the waves
Wait a second. Are you saying and admitting that there's a medium?
Yeah.
How dare you?
This is what I see.
Well, that's one of those things where it's like, okay, we say speed of light in a vacuum, but then when you talk to different folks, it's like, well, what's the vacuum? Well, it's actually rife with frothing virtual particles, and there's an energy density to it. And I'm like, so there's no true vacuum? Or I don't know. It's like, I'm part Irish, so I think I can make the no true Irishman joke. So something like that. That's just kind of the vibe I get there. And I'm just like, you can say space-time, fabric of reality, perhaps a superfluid, but no ether. It's a 5-letter word.
But so
Maybe 6.
The question I have is, the Higgs field makes sense to me.
Okay.
But I have no idea what a Higgs boson is, because when I look, from my point of view, I'm looking at what information does it carry and how does it interact with the other particles. I only have a placeholder in my library because the Higgs makes no sense to me as a particle. And then I'm wondering if you have some way of explaining it to me where I can have any meaning out of it.
See, when you were describing what you were utilizing, I think gravity for within your physics library, there is, it almost sounded like you had things kind of like almost popping out there from that. Now that doesn't really seem like a gravitational effect as far as we know. However, if the Higgs is at least attributed, or whatever we attribute the Higgs to be, to help give mass to other particles, I'm like, well, if you have an energy density suffusing all this different stuff, I'm like, well, maybe, could it be the vacuum? I don't know.
But that would mean that there's got to be some transformation where the Higgs.
It means you have to think of your field as actually being a lattice, and the base cell of the lattice is the Higgs.
That's why it's
Repeat.
crystal and ether.
That's all.
Okay, but then what I'm still missing is there must be some transformation. If the Higgs gives particles mass, where is that transformation?
The Higgs mechanism. I still need to learn more about it and everything.
In each of the cells of the lattice. So any wave that moves through that lattice by going through a cell gets transformed by getting mass or getting rid of mass, depends on which way it went through.
My base rudimentary explanation, or at least from what I've read, and feel free to correct me, I do need to learn a heck of a lot more math and actual setup to this, is usually there's some form of a rotation or something. And very often the way we do rotations is we do e to the I pi and everything, which is one of the reasons why I saw one of those ratios that I just erased over there, where it's like, well, if this ratio between these different top quark and the Z boson, if there was something to it being a ratio of e to the pi or e to 1 over pi, that's interesting. It's also, you could rewrite that as, I think, like negative I to the I or something like that. There's a correspondence there, which I'm like, oh, that sounds kind of similar to what Thad was saying. So should this be surprising? Should it not be? Long story short, Echelon, I got a lot more work to do.
Anyway, I want to say, used to book.
Yeah, one more thing is that since mass has a direct relationship to gravity and the Higgs has a direct relationship to mass, then there must be some relationship between Higgs and gravity. And if there is a graviton, it would be somehow related to a Higgs boson.
Good.
Yes.
All those relationships, when we start graphing, we can use graph theory to put this together.
And again, we also need to be careful because a lot of times as human beings, we also have certain expectations about things. So we want to be careful and just acknowledge when we're making an expectation. That's why I gave it such a crazy name, like the Spherical God Cow. It's obviously a joke. The only reason why I kind of see it as that is just because, like, you're taking something that people in general vernacular say, oh yeah, that God, you say the Higgs boson, it's like, what was that? Oh, that God particle thing. Oh yeah. And then we're just applying the whole concept of literally treating it like a spherical cow, and it seemed to match the data pretty well. Again, it gave a dimensionless number. What that dimensionless number means, you would have to multiply it by meters squared, but then at that point, it's like, you're assuming the meter would have some significance, which I can say it's based upon the constants of nature, but I'm like, did nature know to do that? How the heck could it do that? And that's an interesting open question that I think that hopefully sooner rather than later we'll be able to figure out what's going on.
You know, the Higgs is okay. Sorry, the Higgs gives subatomic particles their mass, but that's just a very small contribution to what's going on inside the atom. So the Higgs is just a little tiny part of the story.
Yeah, most of it, to my knowledge, is binding energy and everything in there.
Right.
And then we get the extra stuff. I think it's usually for like leptons and stuff like electrons, where we assumed it didn't have mass, but it seems to get this little bit of mass there. That's my general understanding. Dan.
I was just going to say the Higgs boson does not occur naturally. We force it into existence.
We need to smash stuff together at extremely high things that...
It's a representation of other things.
We hit a particular energy, and I think the way typically works, again, I'm not a particle physicist, that was Stephen Wolfram, but basically you smash stuff together, you need to have at least the energy to create a particle, whatever that may or may not be, its anti-particle, whatever that may or may not be, and then those end up decaying, and they can decay every once, I don't know, 1 out of 40 million or 40,000 something, magnitudes vary, but you would end up getting things that decay into what we believe to be the Higgs, because we ultimately end up measuring the rest of the photons that are emitted and everything. So that's a rough, I may have missed a step in there, but that's the general way where we're trying to investigate. And again, we have certain expectations in there, and if at least quantum mechanics was able to help us estimate what these decay products should be, that seems like a useful thing to add.
Just for those who haven't ever played this game before, I just want to advertise it for what he's doing here. And he did it really clear. He told you what his assumptions were, showed you the match, trying to make a connection. But the thing he didn't state at the beginning is the game he's playing is basically the same as Dirac's large number hypothesis, where he's looking for connections between the physical parameters. He's not trying to start with a story. He's trying to start with the physical parameters and then look for a pattern. He's trying to step completely outside of my story to try to find out what actually just works for the data. And it doesn't necessarily mean you're leading to something, but when you find connections between certain parts of physics and other parts of physics, there's these huge crazy numbers attached to them, and they match so well. It can at least lead to connections that you might not have intuitively already had a picture for.
Yeah. Oh no, some things I'll find, it's like, oh, somebody figured this out 100 years ago, 50 years ago. It's just playing around, because a lot of times it's like I have a lack of knowledge. I don't have an official physics background. So a lot of this I need to learn from like either folks on the internet sitting down with different of you all and everything. And then just Wolfram Alpha, God bless Team Wolfram, has like the largest unit database. So it's literally like training wheels. So it's like it keeps me from going off the rails. So there's no dimensional interpretation of that. Okay, maybe that's not really a real thing then. And then I just try to simplify it. And then again, one of the biggest benefits is it will show me the relationships in between other things. And that's kind of how I went through this, because it's like, well, this is around the relativistic mass of like 1 joule or something like this, or this is like 137th of the magnitude of Planck's reduced constant, h bar. So I'm like, all right, well, 1 over 137, fine structure. Oh, look, it matches to 9 digits. Okay, cool. So I'm just kind of playing pattern matching game, because the one thing I'm kind of good at is remembering the first couple of digits of something that I see on a frequent basis and approximate powers. And rather than having to go through all these journals and everything, like all like the smart people that passed it, I can literally just ask the question right there. And now if you find something that might be interesting, you want to go in with the most precise measurements, trust but verify, and go through. And like that said, just because it has an interesting match or it's kind of close, it doesn't mean it's actually right. We have to be careful about separating the map from the territory, so to speak, because you can get really caught. Oh, here's a cool calculator. This obviously explains everything. I don't know. So.
And there's also another problem I have with the concept of the Higgs boson in the standard model. Because everything in the standard model has an antiparticle, right? For every particle in this, there's an anti. That means there's an anti-Higg, which means there must be anti-mass. What does anti-mass mean?
Antimatter.
So coincidentally...
Does antimatter have anti-mass, or does it have mass?
Anti-Higgs makes antimatter.
But then antimatter would have mass, not anti.
Yeah, it has mass.
So
There's
then
no
what-
anti-mass.
But then,
Anti-mass is mass. It's always it's a squared thing, so it's always positive. That's all. But still, antimatter and matter are opposites, but they both have the same amount of mass. The electron and the anti-electron have the same amount of mass.
so an anti-Higgs would still impose plus mass.
Antimatter falls down.
Yep.
Regular matter falls down.
So it's, again, I have this written on the shirt in a particular way, but again, full disclosure, if you just plug this in, you set equal to h bar divided by joule second, so you're taking that magnitude. This is a squared answer. To be fair, if you set it up in a different algebraic fashion, you get a positive and a negative answer. So I mean, if there is an anti-Higgs, then it's like, okay, maybe that's the case. I don't know. I heard something about a positive mass conjecture and everything, so I'm like, All right, just to avoid that problem, I just put it on this as a t-shirt. But full disclosure, you can write this in a way where there is also a negative term, just because you have a square in there. So just that, thank you for bringing that up, just because, again, human assumptions, inputted assumption. I'm assuming it's positive, so I just put it this way, but the actual thing, it does come out, it will give you positive and negative answers.
And actually, if there is such thing as anti-gravity, then there must be such thing as anti-mass, I would think. They seem like they would go
If
together.
they would go together, they would. They wouldn't exist.
So yeah, it's again, that's my general understanding, and yeah, exactly. Who knows? Things may vary because again, we want to be open and honest, and that's why I try to be really open and honest. It's like these are assumptions. These are the assumptions I was based upon. Here's the general method that I went through. Whether it's right or wrong, I have no idea, but it seems to line up. And again, if we don't really necessarily have a good story, here's a story. I don't know if it's right, but it's kind of what I wanted to share. So, cool. Anything else? Cool. Thank you. Yay.